Here we're going to continue our discussions of equation of lines. And to remind you about the setting, so let's say we have a vector v with components a, b, and c, and the point P with coordinates x0, y0, z0. And so these two are given, and we want to find the equation of the line for the point P and in the direction of the vector v. And as we discussed on Friday, so this looks like this. So we can draw this on a coordinate system and then get some motivation again for getting an equation of a line. So you have a point P with some position vector. You have a vector V, let's say pointing in this direction, and we want to find the equation of a line that passes through P in the direction of V, and let's just make sure that this happens here. Okay, so the line is L. Then the way that I dealt with this last time, you pick some other point on the line L, and you call the position vector for P R. You call the position vector for that arbitrary point on the line. So for P it's R0. For arbitrary point, this vector is R. And so this shows to you that the vector R minus R0 should be parallel to the vector V. And that means that R minus R0 is equal to some scalar times V. So T is a scalar. Right, because given any two parallel vectors, I can always write one vector as a scalar multiple of another vector. And solving this equation for R, we're going to get that R is equal to R0 plus T times V. And again, the interpretation of this equation that I gave you was that you can think of it as you're sitting at a point R0, you want to move along the line L, let's say with velocity V. So what is your position along line L at the time t? Is going to be your initial position plus the displacement So t plays the role of time, v plays the role of a velocity, and it just describes, this equation simply describes the position of the particle that moves along the line L with velocity v. And so this equation then involves 4 coordinates. One coordinate is time, and the 3 other coordinates will be coordinates of a point in space, with the consequences of that discussed in a moment. So this is called the vector equation of a line. Now we can rewrite this equation in components. And so that means that x, y, z should be the same thing as x0, y0, z0 plus t times a, b, c. So x, y, z is going to be x0 plus at, y0 plus bt, z0 plus ct. So the corresponding components must be the same. And so that means that x should be x0 plus at, y should be y0 plus bt, and z is z0 plus ct. This is a scalar equation of a line, but also you can call it parametric equation of a line. And then in this parametric equation, t is a parameter. Right, because t is not really a spatial coordinate. Okay. All right, let's do an example of this. Let's say I want to find the equation of the line L that passes through the points let's suppose 0, 1, 0, and maybe 1, 2, 3. So what are we supposed to do? Draw a picture. You have 2 points, maybe one here, another here. You want the equation of a line that goes through these 2 points, so that's your line L. And the way to approach it, right, so we know how to get an equation of a line that goes through a given point in a given direction. So in this case, instead of prescribing a point in the vector, I'm giving you 2 points. So the first step that you must make is to find the vector, because both points lie on the line, so you can use either one of these 2 points to find the equation of a line, but also you need a vector. And the vector has to be along the line, and clearly a vector along the line is going to be a vector that is pointing from one point to another point. So it's a vector like this. And to find that vector, you need to take a difference between a position vector to one point and a position vector to another point. And the position vector for a point is the same as coordinates of the point except written in components. So if I call the point 1, 2, 3 Q and the point 0, 1, 0 maybe P, then this vector is going to be PQ if this is P and that is Q. And so vector PQ should be 1, 2, 3 minus 0, 1, 0, which is 1, 1, 3. And so now I need the equation of a line that passes, let's say, through P in the direction of PQ. And therefore, the equation of a line, if I write it in a vector form, is going to be x, y, z, what I called r, equal to, let's go back here for a moment, is equal to r0, components of a position vector to p, times t times a vector abc. So p has a position vector 0, 1, 0 plus t times a vector in the direction of a line, and in this case it's a vector pq, so it's 1, 1, 3. So again, this is a vector equation for L. If I want to find the corresponding parametric equation for L, I simply need to write this in components, and so x has to be equal to 0 plus 1 times t, so x is t, y is 1 plus t, and z is 0 plus 3t, so just 3t. And with that, now I can, for example, again, remember the interpretation that I gave to this? It's an equation which gives me a position of the particle at a time t, and that particle flies along the line L. So at every point it belongs to L. So I can ask where the particle was at the time, let's say 1. So when t is equal to 1, then I have x equal to 1, y is equal to 1 plus 1, 2, and z equal to 3 times 1, 3. When t is, let's say, minus 1, so that means I can figure out where the particle was 1 second before before it passed through the point P. So here x is going to be t times minus t at minus 1, y is 1 plus minus 1, 0, and z is 3 times minus 1, minus 3. So by choosing different values of t, I'll find different points where the particle is on the line, or also just different points on the line. Okay, so then I can ask a question. At what time the particle would pass through Q? Right, because originally I wanted an equation of a line which passes through P and Q, and so to figure that out, let's recall what the coordinates of Q are. The coordinates of Q are 1, 2, 3. So I need to solve the equation. 1 is equal to t, 2 is equal to 1 plus t, and 3 is equal to 3t. And of course, we already know what that is, right? Because I have 3 equations with one unknown. And if the particle passes through the point Q, I just solve one equation. First equation actually is trivial, just t equal to 1. And if t is equal to 1, clearly second and the third equation are satisfied. And we already know this because we figured this out on the previous line, right? When t is equal to 1, then actually your particle is at 1 to 3, which is Q. Okay? So then I can also ask this question. Does the point let's say R with components 1, minus 1, 4 lie on the line L? So how do I figure it out? If it does lie on the line L, then there will be a time when my particle passes through the point R. So what time would that be? That would be a time when 1 is equal to t, minus 1, the y component, is equal to 1 plus t, and the z component 4 is equal to 3t. Well, if that is true, then from the first equation, t should be 1. And I already know that that's probably not going to work because I know that at t equal to 1, I'm at a point 1, 2, 3. And here I have a point 1, minus 1, 4. So if I try to determine t from the second equation, right, then t from there is equal to minus 2. And you notice then this is not the same t. And so that means that I will not be able to satisfy all 3 equations with the same t. And so that means that this point does not belong to the line. So R is not on L. All right, so now let's think of the following situation. Now let's suppose that P has components x0, y0, 0, and v is, vector v is a, b, 0. Again, if I want to find the equation of the line L through P in the direction of V, because both P and V lie in xy plane, their z coordinates are 0, z coordinate and z component are 0, then L lies on xy plane. In other words, this is a line in 2D. Okay, so then my equation of a line is going to be x, y, z equal to x0, y0, 0 plus t, a, b, 0. And if I write this equation in a parametric form, I will get that x is x0 plus at, y is y0 plus bt, and z is z0. So the third component being equal to, not 0, but 0. Third component being equal to 0 simply again signifies that my line lies on xy plane. Well, but we're very well aware of how to find the equations of a line on xy plane. So in this case, I know the point P, and I know V. V gives me the direction of a line, so direction of a line gives me the slope of a line. So I should be able to find the equation of my line simply by using the point slope formula. And the way to do it, maybe again to draw a picture. So we have two coordinates x and y. Z is irrelevant, it's just equal to 0. So you have a point P, and then you have a line that goes through P, and this line is in the direction of a vector. So this is P, this is V, and I'll just write the two components, two non-zero components, so it's just A, B. Now, the slope of V must be B over A, right? It's a rise over run. So the slope, and this is my line L, so the slope should be B over A. So the slope is B over A. P has components, coordinates, x0, y0. So the equation of a line is going to be y minus y0 is equal to the slope, B over A, times x minus x0. Or I can rewrite this also in the following form. If I divide both sides by b, I can write this as y minus y0 over b equals to x minus x0 over a. Well, but this does not look the same as the equation of a line that I found on the left, right? It's this on the left, and this is on the right. Well, the equation on the right just connects x and y components, right? It describes a line on the plane. So if I have a particle that travels along this line, then this equation doesn't tell me anything about, there is no time, doesn't tell me anything about the particle as at a time t. It simply describes the trajectory of the particle. This describes the position of a particle at everywhere on its trajectory because there is time involved. But what if the question is, what is the trajectory of a particle? Would I be able to find it from here? And again, trajectory is independent of time, so I should be able to recover its equation simply by eliminating t. So from the first equation, I get that t is x minus x0 over a. From the second equation, I get that t is y minus y0 over b. There is no t in the third equation. And so then after eliminating t, right, because t must be the same as we discussed, coming out from both equations from both coordinates, so it has to be true that y minus y0 over b must be the same as x minus x0 over a, and z at the same time should stay equal 0. This is called the symmetric equation of a line. So in that sense, the standard point slope formula in 2D gives us a symmetric equation of a line. Okay, so what happens in a general case? So for any line L in 3D, right, so far we looked at the line that lies on xy plane. And so if I look at any other line, then, well, we can just copy our parametric equation of a generic line. I can solve the first equation for t. That gives me t equal to x minus x0 over a. I can solve the second equation for t. T is y minus y0 over b. I can solve the third equation for t. That is z minus z0 over c. And all of these t's must be exactly the same. So x minus x0 over a should be the same as y minus y0 over b should be the same as z minus z0 over c. This, again, is a symmetric equation of a line. Okay, so a line in 3D can be written, its equation can be written in 3 different ways: as a vector equation, as a parametric equation, and as a symmetric equation. All right, let's do some more examples. Find the symmetric equation of the line through the point P with coordinates 1, -1, 0, and parallel to the line with the following equation: x minus 2 over 3 is equal to y plus 1 over 2 equal to z over 5. Okay, so to find the equation of a line, I need to know the point, and I need to know a vector in the direction of a line. So in this case, the point is given to me. The vector is not given to me, but what is given to me is the equation, symmetric equation of a line that is parallel to my line. And from this symmetric equation of a line, I can read off the coefficients of the vector a, b, c simply by looking at the denominators of these expressions here, right? Because this is a generic symmetric equation of a line. On the top, it has x minus components, coordinates of the point P. On the bottom, it has components of the vector v. So, first thing that we notice is that, let's call this line line L and this line M. M is parallel from its equation to the vector v with components 3, 2, 5. And now I want the symmetric equation. Okay, so it's parallel to v, and therefore because L is parallel to M, L is also parallel to this v. Again, I examine the symmetric equation of a line, the way it looks. It has coordinates minus coordinates of my point, components of a vector in its denominator. So in this case, I have v equal to 3, 2, 5. Point is 1 minus 1, 0. So the symmetric equation of my line is going to be x minus x0. x0 is 1. So x minus 1 divided by 3, right? X component of a vector v equal to y minus 1, y plus 1 divided by 2 equal to z minus 0, so z over 5. Right, and that is the equation that I'm looking for. That's a symmetric equation of my line. What if we want to find, so what if we need the parametric equation of this line? Okay, so in that case, I just recall how I got the symmetric equation. I solved the parametric equation for t, and then I set all different t's equal to each other. As I'm going to do here, I'm just going to say that all of these are the same, and they're equal to some parameter s, which means that x minus 1 over 3 is equal to s. If I solve for x is 1 plus 3s. I have y plus 1 over 2 equal to s, so that is y equal to minus 1 plus 2s, and z over 5 is s, so z is 5s. And so that would be a parametric equation. So this describes a position of some particle, right, that moves along the line, and s for that particle will play the role of time. One other thing to notice here. So next example. Are the lines with a symmetric equation, x minus 2 over 2 equal to y minus 1 over 4 equal to z plus 3 over 6, and x plus 2 over 1, so it's just x plus 2, equal to y minus 7 over 2 equal to z minus 6 over 3. Are these lines intersecting? Parallel or skew? Right? Because if we are in 3D, then two given lines can either intersect, be parallel, or be skew. So skew is kind of intersecting, but at some angle to each other, but actually not intersecting each other. Okay, so how do we answer this question? The first thing to look at is the following. So let's call this line L again. And the second line I'm going to call M. I will immediately notice the following. L is parallel to the vector with components given by the denominator of the symmetric equation. So this is 2, 4, 6. And M is parallel to the vector with components for the same reason, 1, 2, 3, right? These are the numbers in the determinants of this expression. Okay, and what do we know about the vectors 2, 4, 6, and 1, 2, 3? So clearly 2, 4, 6 is twice 1, 2, 3. So therefore these vectors are parallel. Right, they point in the same direction. And so the conclusion L is parallel to 246, M is parallel to 1 to 3, 246 and 1 to 3 are parallel to each other. So everything is parallel, so therefore L is parallel to M. So if two lines are parallel, they can actually either be the same line, right? They can coincide, or they can be parallel on some distance from each other. So then the next question might be, do L and M coincide? And if they coincide, then they must have a common point. In fact, all points must be common. So if I pick some point on the line L, it also must belong to the line M. So clearly, again, from the way we defined the symmetric equation of a line, right, the things that I'm subtracting from x, y, and z on the top are the coordinates of a point P that lies on the line. So clearly in this case, point 2, 1, minus 3 belongs to L. Does it belong to M? How do we check that? We simply take 2, 1, 3 and substitute into the equation for M. So we're going to check if x plus 2, so 2 plus 2, if this is equal to, so 1 minus 7 over 2, and where that is equal to z, which is minus 3 minus 6 over 3. And of course, clearly that is not true, right? Because 4 is not equal to minus 3. So this is not true. Although the second equation is true. So therefore, the answer is no. It does not belong to M. And that means that at least one point is not between the two parallel lines is not in common. That means that L and M are two distinct lines. Okay, hope that this is clear. Then one last example for the lines section. Let me see if I want to do anything else besides that example. Actually, let's do one more thing first. Going back to this line L, does the line L intersect the YZ plane, and if so, where? Right, so the question is, I have my coordinate system. So YZ plane is facing us. I have some line, like so. And the question is where it would intersect YZ plane if it does intersect it. Right, because in principle it can be parallel to ZY plane, and in that case it's not going to intersect it. Okay, so if the line intersects YZ plane, that there must be a coordinate, this must be time, where my particle will have x component, its x component equal to 0. So on YZ plane, x is going to be equal 0. Okay, so let's see where would this happen. If x is equal to 0, right, then so again, thinking about the particle. I want to rewrite the symmetric equation that is given to me in a form that describes the trajectory of the particle, and then I would work with the particle, and it will be clear why in a second. So if I want to have a particle, then I need to have a parametric equation. So I'm going to set all of this stuff equal to t, as we discussed before. That will give me now a parametric equation if I solve this for x, y, and z. So x will be 2 plus 2t, y is going to be 1 plus 4t, and z will be minus 3 plus 60. Okay, so I want to see where this thing will intersect YZ plane. So I need to solve an equation. So to find the time when the particle crosses the YZ plane, I need to solve 0 equal to 2 plus 2t, right? I need to solve the equation for the time when x is equal to 0. So in this case, x is equal to minus 1. And then I can find what y and z are at, sorry, it's not x, it's t. I can find y of minus 1. That is 1 plus 4 minus 1 minus 3. And z of minus 1, that's minus 3 plus 6 times minus 1 minus 9. So the answer is the line intersects YZ plane at the point -3, -9. Okay, so, and then the last example is going to be as follows. So determine if the lines L1 with a symmetric equation x minus 1 over 2 equal to y minus 2 minus 3 over minus 1 equal to z plus 1 over 3, and a line L2 with the equation x minus 2 over 3 equal to y minus 3 over 1, so just y minus 3, equal to z minus 2 over 2, if these guys are, again, parallel, intersecting, or skew. Okay, already answered a similar question before. So the lines would be parallel, right, if the vectors along them are going to be parallel to each other. If I've given you two lines in a symmetric form, two equations of lines in symmetric form, again, I can use the denominators to find vectors parallel to my lines. So V1 with components 2, minus 1, 3 is parallel to L1. V2 with components 3, 1, 2 is parallel to L2. Clearly, V2 is not a scalar multiple of V1, right? In particular, because to get from here to here, I must multiply by positive 3/2, but from here to here by -1. So V2 is not equal to scalar times V1, so V2 is not parallel to V1, and so therefore L2 is not parallel to L1. Okay, so then the remaining options are skew or intersecting. If the lines are skew, they don't have a common point. They're not parallel, but they don't have a common point. If two lines are intersecting, then they have a common point. And if there is a common point, if I take a particle that travels along one line, at some point it will pass through that common point. And if I take another particle that travels along the line L2, it will pass a common point. But they don't have to do it at the same time. They will do it at a different time, but they will do it nevertheless. And so we need to go back to the particle description again. And time for different particles might be measured in a different way. So I'm going to use different parameters for different particles. So for the particle number 1, I'll use the time t. So to change the symmetric equation to the parametric equation, I'll set this equal to t. And for the particle number 2, I'm going to use a different parameter name. I'm going to call that s. So the parametric equation of the first line then is going to be x equal to 1 plus 2t, y is equal to 3 minus t, and z is equal to minus 1 plus 3t, right? So that's my line L1. And for the second line, x is equal to 2 plus 3s, y is equal to 3 plus s, and z is equal to 2 plus 2s. So if there is a common point, then there is a time s and another time t such that this particle at the time t is at the same place as this particle at the time s. So the corresponding coordinates at those times must be the same. So 1 plus 2t should be equal to 2 plus 3s. 3 minus t should be equal to 3 plus 2s. And minus 1 plus 3t should be equal to 2 plus 2s. So these three equations would need to be satisfied at the same time. And I noticed I have two unknowns, s and t, and I have three equations. I have more equations than unknowns. So it is possible that I have too much information and that there is no solution. If there is no solution, that means that the lines are skew. If the lines are intersecting, there is a solution, and not only there is a solution, but there is only one solution, because two lines that are not parallel and that are not skew can intersect only at one point. So let's see what situation are we in. So from the second equation, I have that t, if I solve it for t is equal to minus 2s. So then I can substitute that into the first and the third equation, and that will give me 1 minus 4s equal to 2 plus, actually let me do it in steps, 1 plus 2 times minus 2s must be the same as 2 plus 3s, and minus 1 plus 3 times minus 2s, this should be equal to 2 plus 2s. So then from the first equation we will have 1 minus 4s is equal to 2 plus 3s, and from the second equation minus 1 minus 6s is 2 plus 2s. Well, then from this equation I'll get that 7s is equal to, or minus 7s is equal to 1, so s is minus 1, 7. And from a second equation I'll have that 8s is equal to minus 3, so s is minus 3/8. So two equations give me two different answers. So these minus 1/7 is not equal to minus 3/8. So that means that there is no common solution to all three equations. So no solution. And so therefore L1 and L2 are skew lines. Okay, so with this in mind, next time we're going to talk about the equation of planes and give multiple examples of those. Thanks.